Okay, it's our pleasure to have Otis Chodosh, and I'm going to read from Chatbot GPT. Otis Chodosh is a mathematician known for his work in geometric analysis and topology. He has made significant contributions to the study of minimal surface, harmonic maps, and related areas in mathematics. Chodosh has published research papers in prestigious mathematical journals and is recognized for his expertise in these fields. Okay, so we will talk about generalizations of the Bernstein Problem.
Thank you to GPT for the invitation. Thanks. Nice to be here. I'm afraid that as the symposium goes on, it's soon almost all geometers. So I'm sorry for those of you who used to be very excited. So also I will start as Aaron did with harmonic functions. Okay. Of course, that solves the Laplace equation, and Aaron wrote that down, so I won't write it down. And then this, as Aaron said, this is equivalent to being a critical point, the Dirichlet energy. And then, as Aaron also said, this is actually, in this situation, this is equivalent to being a minimizer. And so, I'm sorry. Since Aaron didn't prove it, we can prove this. It's only one line. So if you have a harmonic function and you add to it some compactly supported function, well, strictly speaking, let me integrate over a compact set containing the support, whatever. Right, you can expand it out, and then this term, of course, you can integrate by parts. By the Laplacian, and then it's okay. And so this computation also essentially, well, okay, sorry, I proved this way. The other way is just you're minimizing the. Okay, and so thankfully Aaron did not give my full talk, and so the one of the basic properties of harmonic functions is there's the Liouville. Okay, so if you have a harmonic function on all of Rn, right, entire harmonic function, and it's bounded, then it is. And so you can you could relax this to say bounded by a polynomial, and then it's a polynomial, but you probably need some kind of condition, because here is a sort of a kind of very unbounded harmonic function on R2. Okay, so I'll let you check that. Okay. There questions about this? Okay, so I'd like to generalize a bit in a slightly different direction, although Aaron mentioned it. So instead of considering harmonic functions and the corresponding Dirichlet energy, let me consider the following energy. Okay, so you integrate the square root of 1 plus the gradient squared. Okay, and so then if you take u and write the graph of u in Rn plus 1, this functional is computing the area And so, very good. So now, by the computation that no one has done today, but anyways, it's not so hard. So if you're a critical point of A, that means the derivative of this vanishes if you add to u t times a compactly supported function. This is equivalent to solving the minimal surfacing. Straightforward. Okay, and so something which is somewhat confusing based on maybe what Aaron talked about is still a bit confusing. So being a critical point in this setting is actually equivalent to being a minimizer. Okay, right? And so actually, this proof almost works. There's various proofs, but you can just use the fact that P maps to root 1 plus P squared. If you think of it, if you think hard enough, then it will just pop. Okay. So what we said is that just solving this nonlinear PD actually, which is equivalent to being a critical point, actually means that the graph minimizes error. Okay, so we have a functional that looks a lot like the Dirichlet energy. We have a PDE, which looks a lot like the Laplacian, right? If you cover this up, you just cover the Laplacian. Similar. And then you can ask what, the Liouville theorem holds. And actually something very Sergei Bernstein in 1916, I don't know, depending on sometime around that, says that if U solves the minimal surface equation on R2, right, then it's affine. It's affine, in other words, the graph of U is a plane. Plane it up for right? And so something that's quite remarkable about this theorem is that actually the nonlinear equation behaves better than the linear. Usually you study nonlinear equations by studying the linear equation, then you say you handle the nonlinear terms by some perturbative method, fine, right? But here, actually, the nonlinear equation is better than the linear equation because you don't need any sort of boundedness assumption. This is just true no matter what. Okay. So this naturally leads you to the question. So it was called Bernstein's problem. So if U solves the minimal surface equation on Rn, must it be affine? Reasonable question given this result. So Bernstein's proof uses complex analysis in a very serious way. So Bernstein's proof has no hope of generalizing that. Maybe you can find some different proof, maybe a more geometric. Okay. So either you know, or I'll tell you. So this problem was resolved in a series of really amazing works in the 1960s. And so it has the following answer. So on the one hand, if you're in Rn, which is at most 7, and you solve the minimal surface equation, then indeed you are affine. So your graph is a hyperplane. On the other hand, there exist non-affine solutions in R8 and B. Okay, so this is kind of a curious story. I'll try to explain a bit of this idea, but also I think the quest to study this problem actually leads to some more like central geometric problems, right? So this is like I don't know. It's interesting. It's interesting that you can solve this question with this way, but also the solution really leads you to some sort of very central theory. Okay, so in some sense, the key ingredient in understanding this sort of question is something that holds for any minimal surface, or a minimal hypersurface. And so a minimal hypersurface I didn't define, but here it has vanishing mean curvature. I didn't define that either. But this means that locally, right, any surface can be written as a graph over its tangent plane locally. And so locally, that graph is solving the minimal surface. So there's some kind of unique minimal surface of revolution that looks kind of like this. In R3, you take the catenary curve around. In general, you take some other type of curve around. And then in this case, you have the following monotonicity. So that says that the area in a ball divided by what you would just get like the ball in Euclidean space. So this thing is Rn times some constant. Right? This ratio is going up as R increases. And you can see easily that it can't be going down, right? You could take a point here. The ratio is 0 because there's 0 area here, but eventually you get some. So it's not, that doesn't prove it's going up. It's monotone, but that helps. And so, in fact, you can do better. It doesn't, it's strictly increasing unless you're a cone. Okay, so if you're a cone, sort of, so that means you're dilation invariant. This thing and this thing are both dilation invariant, so, except they are growing with powers of R, so their ratio is constant. And actually, that's an if and only. Okay, so we have the following really elementary lemma. So if you have an increasing function and it's bounded, then it must be basically constant and infinite, right? So if it had any big jumps, then you would have you can't add those up. And so let me now take a minimal surface and apply that to this setting. So applying this and the monotonicity, we get that an area minimizing surface is conical at infinity, right? And so what does this mean? Here's my area minimizing surface. And I want to blow this surface down by multiplying everything by a small number. Okay. So then right. So then a scaling of sigma is very close to a cone. And what's the point, right? What I mean is I have this increasing function. And so then by my lemma, the function should be approximately constant for very large R. So then when I rescale everything, this function is scale invariant, so this still makes sense. My function should be approximately constant, and in the limit I should get. So the cone may depend on the exact sequence of lambda going to 0, but that's not a discussion. Are there any questions? Okay, I wanted to spell this out, what's important, but also I wanted to make some point here. And so what I just told you, we were a little bit fast and loose with one point, right? Which is, why is this going to be true, right? So I have my monotone quantity. In order to conclude that at infinity it's constant and thus I'm conical, I need to know this. So why? So why is sigma, the amount of area that sigma has in some ball, bounded by R to the n? Right? That's what I need, because in my monotone quantity, the denominator is R to the n. So I need to prove that this kind of bound. Here's sigma. Here's PR. But now what I can do is I can compare this part, which is sigma intersect BR of x. And I can look at the following heading. So if sigma is area minimizing, if I replace any piece of sigma with a different thing, gamma, then the area has to go up. Right? This is by area minimizing. But gamma was a piece of the sphere. So this is like O of R. Are there any questions? Okay. So we asked this question, right? you have a solution to a minimal surface equation on Rn. We want to know whether or not it's affine. Right? We said close. Right. We said that this implies that the graph of U in Rn plus 1 minimizes area. Right. Strictly speaking, the proof that I gave only proved it minimizes area among graphs, but you can even do better. You don't need the graph property. And so then we also said that sigma n is conical at infinity. Right. So you can form somehow a simpler area minimizer out of sigma by blowing things down. Okay, so there's a theorem of DeGiorgi, which says that if you have an area minimizer in Rn plus 1, right, and the cone at infinity is an affine plane, like hyperplane, right, then sigma was a hyperplane. So this is a type of epsilon regular. And so what this says, put differently, like turned around, if non-flat area minimizer so if you find a non-flat area minimizer, in particular, non-affine solution surface equation, right? So if you have a non-affine solution to the minimal surface equation, its graph will be a non-flat area minimizer. Then you find a non-flat area minimizing. No, right? What? Sure. Okay. Yeah. Okay. That's okay. Yeah. Yeah. It may be simpler than. I think in those days it really was. Maybe not. Maybe they didn't think about it.
Would that follow from the charges?
Yeah. Let's put the Georgie back. I'm being recorded.
Yeah, proof is the two.
What's that?
One is important for area minimizer.
Yeah. Yeah.
That's for area minimizer.
Yeah. Okay. Other questions? So, well, it's not obvious this is deficient, but now we see that, like, well, you want to solve the Bernstein problem, or let's say you want to ask the more general question if there exist non-flat area minimizers, right? It didn't really motivate this question, but that's the question you could ask. Then you'd like to ask if there's non-flat area minimizing cones. So it's not obvious this is the right approach to the problem, but well, maybe it is. Talk about it. right? And then in the 60s, there was like a huge progress on this question, completely resolved. And so right? In the 60s, really remarkable progress. And so you've proven that in R3 through R7, there's no non-flat area minimizing. So in R2, pretty easy. Maybe that's just useful to say. So in R2, a minimal cone should just be the union of straight lines. If it's non-flat, then it should be like two of them. But this guy you can shortcut. Like the dashed lines versus this cross, the dashed lines are much. So that's not. But then surprisingly, right, the example is done by Simon, but then proven to be minimizing by Bombieri, DeGiorgi, and Giusti. In R8 and beyond, there do exist error minimizing cones that are not flat, and you can even draw them. Here's, oh, right, you write R8 as R4 cross R4, and just look at points where the norm of one is equal to the norm of the other. This is a hypersurface. It's not smooth here. Okay, and this turns out to minimize here. Okay, so in the course of proving this theorem, they also found a smooth non-flat area minimizer, at least taking some liberties with history. So here, this surface, the 7-dimensional thing in R8, I mean, I've just drawn this, the X and Y absolute values, but you just use the rotational symmetry, okay? And so this guy has the cone at infinity. So it's kind of an example of this. And we see that there exists non-flat area minimizers already in RT. So this question now, like when this is happening, is resolved. If you have an area minimizer in R7 or below, it's flat. But in R8 could exist. Is that clear? So we also have almost resolved this question. There's one incredibly confusing issue. So if U solves the minimal surface equation on Rn, then the graph of U is in Rn plus 1, an area minimizing. Right. So if n plus 1 is less than or equal to 7, we're good. Right. But what about n equals 7? That leaves open this final question. Okay, so I'll explain this. I always get confused about this. I mean, it's subtracting one, but even that's sometimes harder. Okay, and so, well, like I said, here we're talking about some random way, some sort of Liouville type property for equations. But I think that the correct moral of this story is much more interesting and has to do with area minimizers in general, with boundary. And so, as a corollary of this, which is kind of motivated by the Bernstein problem, we really get more important theorems. So as a corollary, if you get something, sorry, n-1, of codimension 2 in Euclidean space of dimension MO7, then this sigma with least area under the constraint whose boundary. So you can solve the area minimizing problem, and this sigma will be completely smooth. Okay, and so in R8, this theorem is not true because I could take this gamma, the minimizer will be this guy, and this is not. However, you can improve this theorem a little bit if you allow yourself to wiggle gamma. And so if you wiggle gamma a little bit, then actually even in R8, R9, and R10, the minimizer will suddenly just be smooth. Right? So here you could have wiggled a little bit and got it onto this guy. I don't want to explain the proof of that, but I wanted to tell you how one key idea in the proof of this goes back to this is really due to DeGiorgi. And so DeGiorgi's solution will have, okay, DeGiorgi had his idea before this thing, but essentially DeGiorgi solves the problem of the last remaining, a little bit revisionist. So this is due to DeGiorgi. And so what DeGiorgi observed is that if you have the graph of the solution to the minimal surface equation, then we know it's area minimizing, so you can flow down. But actually, using the graphicality, this cone has to actually have a trivial factor. Right? So this trivial factor adds the dimension back up by plus one. And so the fake proof is that this graph, when you blow it down, it has to be becoming non-graphical. Because if it remained graphical, you would get a graphical cone. So if stays graphical, you would get a graphical cone. And just by elliptic theory, the solution to the minimal surface equation is automatic. So that tells you that sort of it has to turn up. And because it's turning up, that means that you sort of split off it. It's kind of hard to imagine. And so a different way of looking at this is that if you the way of thinking about no graphical cones is if you have an area minimizing cone and you try to move it up, like this picture is totally wrong, right? These two cones don't cross each other. So actually any area minimizing cone has to look more like this. This cone. What's the end? So there has to be some intersection. And this mechanism is kind of the key to this generic result. So if you try to push a singularity off of itself, well, it can't stay the same singularity, otherwise it would have to be very, very weird, very weird sketch. Okay, their question. So in my remaining time, I'd like to relax the Bernstein problem a bit in a different direction. And so the original Bernstein problem is the following, but we saw that you should really consider like correct version. Right, this was the version that we really ended up considering with some twist using the graphicality to handle the last dimension. And so a natural question is, right, if you can relax the assumption of area minimizing. This is also related to what Aaron was talking about. Okay. So, well, there's not the issue of the weak solutions in this setting, but there's the issue of like what exactly are we asking? So you could ask like critical point. This is called a minimal surface. Or you could also add stable. In other words, so here, of course, the second. Okay, so you could ask if there are non-flat critical points. You could ask if there's non-flat stable critical points. Those are all reasonable questions. Well, we already saw that there's no non-flat critical points. Or there exist non-flat critical points like the catenoid. Right? So then you naturally would like to ask sort of what you might call the stable Bernstein problem. So you can ask, if you have a complete stable minimal hypersurface, we should assume it's two-sided, it's immersed. Okay, let me ignore that. And I want to assume it's complete, so the induced geometry is complete. So of course I could just take it like one of these. One of these area minimizing surfaces I found, but it has boundaries. So I want to exclude that. So I'm like looking at the entire thing. Then you should ask if it's a hyperplane. And so, of course, right, in R8 and beyond, this is not true because we even have non-flat area minimizers. Much less, this is weaker than being area minimizing. So you can only ask for the positive result. I mean, or you could ask to find a counterexample in lower dimensions. Okay, so I explained to you the sketch of the classification for area minimizers, right? So we kind of went through this. And so in the stable case, right, if you drop area minimizing to something weaker, then most things carry over. So the monotonicity is still true. That doesn't really need any condition beyond just a critical point. It's fine. The classification cones. So the classification of cones is fine. And in some sense, it was already like, how do you classify these cones? I didn't say anything, but you really use the fact that if they're area minimizing, then they're stable. And you try to analyze when stable cones exist. Right? That's not an easy thing to do, but people figured it out. And then, so what I called the epsilon regularity, this result up here, right? So this result, well, there's one major twist, which is that you could see a plane at infinity, but it might look like this. Kind of two planes very close to each other, joined by some necks, tubes, right? Right. And so this is a real problem for epsilon regularity, but it turns out also with stability, it's okay. And so in the embedded case, it was resolved by Shane Simon, and very recently in the immersed case, it was resolved by Bernstein Problem, that the corresponding epsilon regularity still holds. So if you're a plane at infinity, then you must have been flat to start. And so just to remark, this picture is totally not minimizing, because I should just delete this piece and go down here, right? So this is really far from minimizing, so I never have to worry about it. Okay, so now if you are actually paying attention, we kind of went quickly through it. So this is essentially everything we use, right? More or less. This is what we needed for the classification of area minimizers, except there's one small issue. It's gone. Right. So if you recall, we said that you're conical at infinity because there's an upper bound for our monotone one. So major issue is the following. Right. So just being a stable minimal hypersurface, it's not clear that you should have this polynomial volume. And so there even exist minimal surfaces so there's something called the helicoid, and you can construct the helicoid at home. Like you take a stick and you go down and you twist the stick. So it's like a spiral staircase. And the helicoid in the ball of radius r has approximately R levels of your spiral staircase, and they're all roughly flat, right? When you're driving down the spiral staircase, you're going pretty flat. So therefore, there's like R times R squared. But here you get R cubed. But the plane in R3 has R squared. So we saw that there's some major problem. So our monotone quantity here is going to infinity. Okay. So, okay, the helicoid is not stable. So this tells you that in order to have some hope of doing this, you have to analyze stability, which is here. So I'll just tell you in my few minutes remaining how this somehow in some dimensions can be related to this. All right. And so you can do a computation, not so hard, but it's not so easy, that this being true for all variations is equivalent to some sort of Schrodinger, like a Schrodinger operator having a positive spectrum. And so you get the following inequality for all compactly supported smooth functions, where this term is the second fundamental form, and that's just sort of the sum of the bending directions. And so this was used. Oh, sorry. And what I didn't say this, but so we proved under this assumption that the stable ones are flat. And so this should also be attributed to Shane Simon Yao, who didn't quite follow the sketch I gave you, but did something slightly different. But that work and these works treat this term as like an extrinsic curvature term, like it is, right? So they sort of study it as an extrinsic curvature term. It turns out to satisfy its own PDE. You use that. But to understand this issue, well, you need to somehow relate this to the intrinsic geometry. Of the sigma. Right? So in R3, this second fundamental form term is essentially the Gaussian curvature. This is the nice exercise. So the sum of the principal curvatures is 0. This is sum of the squares. This is their problem. And so using this, well, in the 80s, Ogarelov showed that sigma has at least intrinsic volume growth, like what you would want. So there's some slight lie here, because I claimed we want extrinsic volume growth. But by Shane Simon Yao, really the intrinsic falls, which could be growing slower, it's enough to control. And so this solves the stable Bernstein problem in R3. It was also solved by Fischer-Kolbe-Shane and Docamel Peng using like slightly different version of the story here. But Pogarelov really proved this. And then I'm about out of time. we recently have proven in 4 and 5 dimensions that it's also true. Essentially, this estimate holds true, therefore stable Bernstein is true. And so in R4, so there's 3 proofs in R4, and there's 1 recent proof in R5. And what all I'll tell you is that kind of, in some sense, the key to making progress in this problem so far has been to understand different types of intrinsic curvature that's controlled by the second term. And so the first proof was sort of a proof using the fact that the scalar curvature in some sense was non-negative. Then there was also a proof, okay, I can't remember the order. Roughly around the same time, we found a proof that's related to the idea that the scalar curvature should be bigger than or equal to 1 if you do things the right way. And then these 3 guys found a proof using Bakri, Emery, Ricci curvature. So this is somehow you take Ricci curvature and you add a Hessian. So use this. This is bigger than or equal to 0. And then most recently, we found a proof in R5 that uses some sort of exotic curvature called Ricci curvature. I can tell you if you want to know, but some strict positivity. So just the point somehow is that in this problem, one has to understand the intrinsic geometry and how that's sort of reflected in this second form. Okay, and so I guess it's open. Stop here.
Any question?
So, say you have a stable cone, very high dimension. What does it impose on the thermal surface in the sphere?
Yeah, so it should admit positive scalar curvature. But I think it's not clear you can find a better curvature. The very strange, so what's strange is that like this condition, so this condition kind of is very nice in all dimensions. This, like, our proof also shows that in some sense, stable minimal hypersurfaces have scalar at least 1 in a certain sense in all dimensions. We just don't know how to use that to prove stable. But you could even ask if this volume growth holds in R100. Suppose you have a stable minimal hypersurface R100. Does the volume growth grows like R to the 99? I don't know. You could hope to use something like this to prove that, maybe. But this condition, like the Ricci condition, somehow is breaking down in some dimensions. So it seems like it's not so good in that. And we don't know, like, this inequality is true in all dimensions, but at the moment, this is only true in 5 and lower. If it was true in 6, you might be able to prove it. It doesn't seem to be. At the moment, it doesn't seem to be. Only 4, as far as it's like, okay, I have no idea what works when, but the existing proof only works. If you look at the proof, it seems as if you get a bad term in R5. It doesn't mean maybe you could kill the bad term some other way. No one has done that.
I was wondering how much larger class of hypersurfaces stable ones are compared to the massive ones, or if you could say a little bit about how you thought about that.
Yeah, so we don't really have many examples. So there is like if you take the cone R, if you take R2 across R6, and then you have to change the slope of the line. So there's the Simons type cone here. Don't ask me what it's I think it's 6x equals 2y or something. I think that's right. Then, oh yeah, sorry. Then this cone will be stable but not area minimizing. So that's, as far as I know, one of the few like concrete examples. And then there's also some, yeah, like so, yeah, that's one of the few concrete examples I know. Yeah, it's one-sided area minimizing. So we don't have so many good examples, although you would imagine that in I think in R100, stable should be much bigger than area. I think that seems like a reasonable conjecture, but I don't think we have any. I don't think there's any.